All right, so again, thank you everyone for joining us today. My name is Miss Selena or Missy from Antec Controls. I am the technical sales engineer on the team, and I have about more than 5 years of experience with designing critical spaces. So for anyone who was able to attend the first session on Tuesday, we talked a little bit about the different types of airflow control devices, and recommendations specifically in labs. Today we're going to be moving over from mechanical, talking more about the control side, and talking about room pressurization solutions in these critical spaces. And again, we're going to focus more on lab design today. So just to start off, we're going to talk a little bit about some background of critical spaces and the room pressurization and what that means. And then we're going to go into fume hood control and talk about how we control airflow through a fume hood through either open or closed loop options. And then we're going to take a step back and take a look at the bigger picture and look at how we pressurize the entire space of a lab. And then again, for this one, we have open and closed loop options as well that we'll discuss. And then based on all of those different factors and options, we're going to go through a lab design example where we'll look at different factors and considerations when designing a lab space, and then calculate the airflow requirements based on each of those factors to balance out a lab space, and then select the correct airflow valve sizes for a specific application. And then lastly, I'm just going to touch on the differences between room pressure measurement, monitoring, and control. This is really important with regards to critical spaces because the pressurization of the space is very important. So just knowing the difference between each of these types of language, and then also knowing what the type of equipment or hardware that's required in relation to each of these, I guess, definitions. And throughout the presentation today, I will be talking or referencing specific standards. So I'll be referencing NCZ 9.5 quite a bit, the ASHRAE 110 standard, ASHRAE Laboratory Design Guide, and also the ASHRAE HVAC Applications Handbook. Like Matt mentioned, we feel free to ask questions throughout using the chat function in GoToWebinar. I'll leave some time at the end as well to address questions if we don't get to them throughout the presentation. So just to get started here, again, when we're looking at these critical spaces, we're concerned with the pressurization. And when we talk about pressurization, we're specifically talking about the direction of air from clean to less clean spaces. So NCZ 9.5 does say that the airflow shall be from areas of low hazard to higher hazard unless the laboratory is used as a barrier facility, such as a clean room. So what that's saying is that essentially we're going to consider the corridor the cleanest space or the cleanest air. We're going to consider the corridor the cleanest airflow, and we want that airflow to go into the lab space and then from the lab space out of the fume hood exhaust. And the reason for this is because we don't want any of the potential contaminated air or fume hood exhaust to leak back into the building and affect other users in that space. So again, we want to make sure we have that direction of airflow from clean, the corridor, to the lab space itself, out the exhaust. Now, when we're talking about clean room applications, these are typically what we would say positively pressurized spaces. So in this case, the experiments or the procedures done in the space itself do need some sort of protection from any contaminants entering the space. Clean rooms will still have typically a fume hood of some sort. That fume hood will be exhausting air itself, but the entire lab space will be positively pressurized so that there aren't any small particles or contaminants that affect what's happening in that lab space. So when we talk about pressurization, and we essentially introduce this, by creating a difference between the supply and the general exhaust valve. So we'll talk a little bit about room pressurization in a bit and how we achieve that difference. But as long as your supply and general exhaust is different, you're going to have some sort of pressurization. If you have more supply, you'll have a positively pressurized space. If you have more exhaust, you're going to have a negatively pressurized space. In addition, air changes can be reduced when your room isn't being used. So when you have let's say a negative lab space, we are able to reduce the air changes to save energy, but we want to make sure that that space still remains negative, even when it's not occupied. Lastly, when we talk about pressurized rooms and pressurized spaces, we want to make sure that there's no large leaks or gaps where airflow can escape through. So we're looking at designing tightly sealed rooms. So here on the right, I have a chart that just shows the different amount of leakages and the differential airflow required to make up for a certain hole in the space or a certain amount of leakage based on the differential pressure between the lab space itself and then an adjacent hallway or reference space. So let's say we have a differential pressure between the lab space of 0.01 and the hole or the leakage size is about 0.5 square feet. If we interpolate and go down that graph, you can see that we need at least 125 CFM to offset that small open area. So again, just something to keep in mind, tightly sealed rooms or perfectly tightly sealed rooms is very difficult to accomplish in design. And ideally, most of them will, not ideally, sorry, but most of the time, some of them will still have a little bit of leakage, which is typically acceptable. You just want to account for that in your offset calculations or your airflow calculations. So going into the room itself, again, we have fume hoods in a larger space, and the fume hoods in these spaces act as primary containment. So these fume hoods are used to protect the users in the lab from any chemicals or harmful airflow that could potentially roll out into the lab. So these fume hoods are meant to exhaust these fumes or these chemicals so it doesn't affect the user in this space. And typically this is done by controlling the face velocity or the airflow through the open area, through the open sash of the fume hood itself. And then when you take a look back or take a step back, the next form of containment or the next step of containment in lab spaces is the space itself. So in a negatively pressurized space, if a chemical spill or emergency were to happen, we want to make sure that the space itself is also pressurized properly. So again, there's no potential for any contaminants leaking out of the space into the rest of the building. The last two factors here, thermal comfort and energy efficiency, both are going to be factors that we're going to discuss a little bit more about throughout this presentation. But it's really important to note that although thermal comfort and energy efficiency are taken into account when we are calculating airflows and design airflows and requirements in the lab, these will not take priority over containment in these critical spaces. Because these critical spaces, again, are essentially ensuring life safety, our primary concern, our primary goal is the fume hood flow and the pressurization of the lab itself. Thermal comfort and energy efficiency will come after once we can make sure that we meet the containment requirements. So starting off with fume hoods, again, just reiterating, the primary goal of fume hoods is to protect the user by maintaining a specific face velocity through the fume hood opening. So ANSI Z9.5 does say that design face velocity for lab fume hoods are typically going to be between 80 to 100 feet per minute. And this is just a recommendation. ANSI Z9.5 does also have a list of other face velocities that could be used and reasonings why they could or could not be applicable to the specific application that you're working on. But for the most part, we do see 100 feet per minute as a target. We do see it go as low as 80 feet per minute in occupied mode as people are trying to target some energy efficiency solutions. ANSI Z9.5 also does say that hoods with excellent containment characteristics may operate adequately below 80 feet per minute. So again, if the fume hood is properly sealed and has good performance characteristics as defined by the hood manufacturer, it may be able to operate as low as 80 feet per minute, but it really does just depend on the performance of the fume hood and the requirements there. If any of you were able to attend the session yesterday that Matt presented with Greenheck, he did introduce two different types of fume hoods, constant volume and variable air volume fume hoods, and I'll touch on that a little bit today as well. And then also considering different types of fume hood sashes. So a vertical sash is essentially a fume hood that has an opening that can only move up or down. A horizontal sash is essentially horizontal panes that can only move left and right. And then a combination sash is a combination of both, where you can move the sash both up and down, but that also has horizontal panes that you can move independently of left and right, independently of that vertical sash. And we'll talk a little bit about how we can control variable air volume hoods with these different types of sashes. But first, again, talking about the different types of fume hoods first. So the first one is a constant volume fume hood. So that's what you see here. We have a sash, we have the airflow entering the fume hood, and then you can also see we have a bypass area at the top of the fume hood here. So as the hood closes, or sorry, as the sash closes on the hood, the total airflow entering the fume hood decreases. But you can see that as the sash closes, the amount of airflow entering this bypass area will increase as well. So the total airflow entering the fume hood is still going to be constant, which means that this airflow control device serving the fume hood or exhausting airflow will always be a constant airflow or constant volume airflow valve. So typically these fume hoods are designed so as this hood or as the sash closes and opens, that opening or that bypass area opens and closes linearly or proportionally as well to make that a more accurate type of control. Now variable volume fume hoods is what we're going to focus more on when we talk about fume hood control. So in this case, you can see that there's no bypass area, and instead there's only one opening for for airflow to enter the fume hood here. So as the sash closes, the total amount of airflow allowed into the hood also lowers as well. So this is truly a variable air volume solution where we have an airflow valve serving this fume hood that's going to change its airflow target depending on the open area of the sash in order to maintain face velocity. So again, these types of variable air volume hoods can have vertical, horizontal, or combination sashes. So when we talk about fume hood control, there are three main types of fume hood control. The first one is sash position control. The second one is sidewall sensing control, and then the last one is hybrid, which is just a combination of the two. So starting off first with sash position control, this is going to be our open loop option. So this is where we are just measuring the height of the vertical sash, and the width of the fume hood, the open width, is pre-programmed into the software. So based on the width and the working height of the fume hood, we can calculate what the open area is in this fume hood. And based on this open area, our controller knows what the airflow exhaust needs to be in order to maintain the face velocity target. So sash position control is open loop because it's just using that calculation, this calculation right here, the open area times the face velocity target. And it's just using that to determine what the airflow should be. But once it's hit that airflow, it's not making any small adjustments based on the number of people in front of the hood, any obstructions, even horizontal sashes. It is really just looking at the height of the sash. So if the height of the sash doesn't move, airflow valve's not going to move. And that's why it's open loop, because it's not going to make any corrections based on what the true face velocity is. However, with that being said, typically sash position control is the most common on vertical sashes just because it is quick and it's simple and it is relatively effective. So just using an example here with some numbers and some assumptions about the dimensions of the hood here. Again, we're going to try and target 100 feet per minute with a working height of 18 inches. Using that airflow equation there, plugging in these values, we can see that the total airflow required through this fume hood is 600 CFM. So at a working height of 18 inches, in order to maintain 100 feet per minute, your airflow valve is then going to move to modulate to 600 CFM, and then just stay there until the sash height moves again. The second type of fume hood control we have here is sidewall velocity control. So this is going to be our closed loop option, where we're continuously measuring the differential pressure between the inside of the hood and then the space itself. So this is closed loop control because we are truly measuring the face velocity, and if that face velocity doesn't match what the target is, it's going to move the airflow valve, or the controller is going to move the airflow valve a specific amount. And then it's going to measure that differential pressure again, compare it in the controller to the target face velocity, and then move the valve, and then do that closed loop control continuously. So again, for anyone who attended session 1, that's very similar to the closed loop control, that the high accuracy terminal unit and just a standard VAV box uses, where again it's measuring pressure, comparing, moving, measuring, comparing, moving. And even once it does reach its target face velocity, it's still going to continuously measure that pressure just to make sure it's supposed to stay at that same position. So one of the benefits of sidewall velocity control is that because it's actively measuring that differential pressure, it can compensate for any obstruction. So as there's a different number of people in front of the hood, different amounts of equipment, if it is kind of like this hood that you see here on the screen, where there's lots of different chemicals and potential obstructions that are affecting the open area, sidewall velocity control is going to be able to compensate for that. Now, one of the disadvantages of sidewall velocity control is the fact that it is sensitive to what's called cross flow. And this is essentially just any unintentional airflow moving past the sidewall sensor that doesn't reflect the normal operation of a fume hood. So this would be high traffic areas where there's lots of people moving or walking by the hood, or a hood that's maybe potentially right beside a door. It could also mean diffuser placement. So in this case, on the bottom here, we have 2 examples of diffuser placement. The one on the left is where the diffuser is blowing air parallel to the fume hood, which is our recommended orientation. And then the one on the right is where we have a diffuser blowing air directly into the fume hood. And this is what we want to avoid, because with sidewall velocity sensors, having that direct airflow is going to create some fluctuations in your pressure reading. And even with sash position control, where we're not actively measuring that differential pressure, this can cause an unsafe environment, because if you blow air directly into the fume hood itself at typically maybe higher velocities than what's normal, it can cause some turbulent flow, and it can cause some backspill of that potentially contaminated air to reach the occupant, fall out of the fume hood, and then reach the occupant. So just want to make sure that any diffusers aren't blowing directly into the fume hood, and if there are, that they're placed an adequate distance away, where the velocity of air isn't going to affect that, that reading. Looking at the third option now, which is called hybrid control, this is going to be a combination of both sash position control and then a sidewall velocity control. So it uses both sensors. And it utilizes the speed of the sash position sensor. So once that vertical sash opens, it's going to drive that valve to its initial position based on the height of the sash. And then it's going to use a sidewall velocity sensor to make smaller adjustments based on different number of people, different amount of obstructions, potential horizontal pains, and those sort of factors. So typically hybrid control is going to be the most accurate. But also one of the disadvantages is the fact that because now we have 2 pieces of equipment, it is a little bit more expensive up front, and it really is only recommended for combination sashes. So just a summary here of the three different types of fume hood control. We've got sash position control, which is quick, it's stable, and it's simple, again, because it's just using that airflow calculation. But the disadvantage is that it can only be used on fume hoods with vertical sashes, and it doesn't compensate for any obstructions in front of the hood. So with that being said, of course, sash position control, like I mentioned, is still pretty much used 90 to 95% of the time with vertical sash hoods. So it is still the most common approach, again, with vertical sashes. And then we have sidewall velocity control. So some of the benefits is that it can be used with all different types of fume hood sashes, and it's also more accurate than sash position control since it's continuously measuring that face velocity. Disadvantages include tuning. So with any closed loop control, there's going to be a PID loop that needs to be tuned and adjusted. And if that's not done correctly, it could potentially result in hunting. But if it's done properly, it's going to work, of course, as intended. And then, like discussed, sidewall velocity sensors are sensitive to cross flow and can potentially fluctuate if there is high traffic areas or a high amount of air velocity pushing or directed at the sensor itself. And then lastly, we have hybrid control, where it uses the speed of sash. It's accurate by using the sidewall sensor, and it can also be used with all fume hood types. And again, because it's closed loop control, it does require tuning, and the initial cost of equipment, like I mentioned, is a little bit higher because you're purchasing both the sash position sensor and the sidewall velocity sensor, instead of just either or. So regardless of the type of fume hood control that's used, sash, sidewall, or hybrid, there can still be considerations for energy savings when you're looking at fume hoods. Specifically, again, variable air volume fume hoods, where you are able to change the open area and decrease the air volume if needed. So this essentially just means that we're safely decreasing the fume hood face velocity target in setback and unoccupied modes. So ANSI 9.5 does say that the cost of ventilation is approximately $3 to $9 per CFM per year, which can get quite costly in lab spaces with lots of fume hoods that are exhausting air constantly, especially for constant volume fume hoods. So it does provide a recommendation that if you are attempting to save energy and you're in high density or you're in labs with higher hood densities, that it recommends having hood air changes anywhere between 150 to 375 hood air changes per hour. Now, depending on the size of the fume hood and the open area, this can typically result in about 60 to 80 feet per minute, which is what you might see in some sequences or some specifications when we're talking about fume hood unoccupied mode. But again, this is just an approximation. The 60 to 80 feet per minute isn't in the standards itself. If you're looking at designing a fume hood at a lower face velocity than 100 feet per minute, you want to look at the 150 to 375 hood air changes and use that as a guideline. And when we talk about setback and unoccupied modes, these can typically be triggered via or through an occupancy sensor that you can see here on the screen. So here we have an occupancy sensor at the top of the fume hood that can detect whether somebody is in front of the hood, or if somebody leaves, it's going to turn back and turn down the target face velocity. So the occupancy can also be triggered through scheduling over the BAS, or again through this occupancy sensor. It really just depends on how the owner or the end users want to use it. And now, before going into room pressure control, I just wanted to touch on some of the other types of equipment that you might see in a lab that you might have to design around. So there's typically snorkels, sometimes even biosafety cabinets. Snorkels are typically used to remove non-toxic and non-chemical or non-corrosive type of fumes. So heat, smokes, sometimes even smells on these benchtop type applications. And then biosafety cabinets are typically found more commonly in compounding pharmacies, but depending on the type of lab space, you can also have a biosafety cabinet there. But one thing to note about biosafety cabinets is that they aren't fume hoods, so they don't have changing sashes that you can move up and down or side to side. Typically, they'll have doors that you can open or close, or they'll look something like what's shown on the screen here, where you're really not even opening the full area of the biosafety cabinet itself, and it's just constantly exhausting a certain amount of airflow. So in both cases, there are two ways you can operate a equipment exhaust. So you can have constant air volume or a two-position operation. And so constant air volume is exactly that, is that we are constantly exhausting the same amount of airflow. So what we see here on the screen is a mechanically set constant volume Venturi valve here. So this doesn't have any actuators, there's no controller, and what's happening here is that this position of this entire cone spring assembly is fixed at 1 CFM. So let's say the snorkel is designed to have a 200 CFM exhaust. This valve is going to be tested in the factory, and then it's going to be positioned at 200 CFM. And then it's going to be shipped without any controls or actuator, so it will constantly exhaust 200 CFM. And then because it is a mechanically pressure independent device with that cone spring assembly on the inside, it's going to be able to maintain that 200 CFM as there are changes in duct static pressure that are introduced. Same thing with two-position operation when you're looking at a Venturi valve. Instead of having a fixed linkage here, what we're going to have is a two-position actuator with a relay. The actuator is going to have hard stops at the min and max airflows. And based on a switch or even a sensor potentially, you can change the two-position actuator to go to its maximum position as defined by the hard stop there. And then if you flip that switch off, you can have that valve turn down to its minimum position based on the hard stop on the minimum side. So in both cases, you don't need a controller, again, because this valve is mechanically pressure independent. It's going to be able to maintain the airflows at each of those states, regardless of the duct static pressure. So that's another reason why we also recommend Venturi valves instead of high accuracy terminal units in these types of spaces, because there's the flexibility of different configurations depending on the type of equipment you have in that space. Whereas if we were to use a high accuracy terminal unit, although we have the accuracy there, we will always need to provide it with a controller and an actuator, whether it's doing constant volume, variable air volume, or even two-position control. So now moving on to the room pressure. So again, we talked a little about the primary containment, which is the fume hood itself. Now looking at the entire lab space itself, which acts as secondary containment. So we can do room pressure control one of two ways. We can do a volumetric offset control, which you can see here is our open loop option. And then on the next slide, I'll talk a little bit about direct pressure control, which is our closed loop option. So volumetric offset control, as you can see here, we are targeting a specific offset between the total supply entering the space and the total exhaust entering the space. And what we're doing is we're looking at what only the measured supply and the measured exhaust. We're looking at, again, supply, general exhaust, equipment, fume hoods, any sort of that type of airflow coming into and out of the space, and we are just targeting to make sure that that difference between the total supply and exhaust always remains the same. So as seen in this chart here, as your flows or your demand for ventilation or your air changes increases, decreases, and then increases again, regardless of the state of that space, you're going to be targeting the same offset. So you will always have, for example, 200 CFM offset in this space, regardless of this, the state. So offset control is independent of room pressure, so we're not actively measuring room pressure and using that to communicate with the controls or the airflow control devices. We are just, again, looking at that offset and using that calculation between the supply and the general exhaust. So again, because it is an open loop control, because it isn't double checking what the pressurization is and then reeling that back to the controller. It just looks at the measured airflow into and out of the space and then just make sure if it's meeting its offset, it's good to go. So this is typically the most common solution in lab applications because it is simple and it's quick. So when you have lab spaces with lots of variable volume fume hoods that are potentially opening and closing, having this quick and simple solution for room pressurization is very beneficial because your room is essentially reacting almost as quickly as the fume hoods are changing as well. In these cases where you do have volumetric offset control though, a room pressure sensor and a door contact switch can still be used for monitoring. So these can be used to install and monitor the state of the room, to monitor to see if you are still maintaining pressure, but it's not actually going to interfere with the control of the airflow valves. So if your room pressure is, let's say, drops below a specific amount, your valves are still going to be targeting that specific offset, but at least you'll still have an alarm to let you know that you're not maintaining pressure. Same thing for a door contact switch. If that door is left open, you're not going to be maintaining pressure. An alarm is going to go off, but again, because that door doesn't have any sort of airflow measurement across it, like an airflow valve, the valves and the controls still thinks it's within the, it still thinks it's meeting offset and maintaining pressure in that space. So when we look at direct pressure control, this is our closed loop option. And this is where we do use a room pressure sensor and we're using that reading to compare with the target pressure. So again, this is closed loop control. So we are measuring the pressure, we're comparing that to the set point in the controller, moving the airflow valves a specific amount, and then measuring, comparing, moving, measuring, comparing, moving, and doing that constant closed loop control. So in this case, it is completely independent of room offset. So we aren't looking at the measured airflow coming in or the measured airflow leaving the space. We're just concerned with the target pressure. But similarly to offset control, regardless of the state or the mode of this space, we are always targeting the same differential pressure. So in occupied, if that space is negative 0.01, in unoccupied, it should still be negative 0.01. So in this case, of course, room pressure sensors are required, and door contact switches can also be used to interfere with the control of the airflow valves. So ASHRAE 170 does say that short-term excursions from required pressure relationships shall be allowed while doors are moving or temporarily open. So what that means is that it's not expected for us to maintain airflow or maintain pressurization in the space while a door is open. So when we have direct pressure control and a door does open, our pressure sensor is going to be able to detect that and it's going to try and move the airflow valves to accommodate for that change in room pressure. But if we had door contact switches, we can tie that into the controller. Once that door opens, the valves are actually going to freeze in place. So it's going to freeze the control algorithm while that door is open, and then when that door closes, that controller is then going to resume the control of the airflow valves. And this just allows for a more stable system, so you don't have your valves opening and closing constantly as people are entering or exiting your space. Typically, direct pressure control is more common in pharmacy applications because of the new USP standard where it is trying to target a specific pressure range in some pharmacies. But for the most part in labs, when we're using direct pressure control, because it's using that closed loop system, as one person opens a fume hood and that and your controller is trying to recalculate the position of the airflow valves to maintain pressure, someone else could open another fume hood and then it will have to recalculate. So it's just not as quick as offset control in spaces where you have lots of fast acting equipment or fume hoods. So looking at air change requirements, the ASHRAE lab design guide does recommend anywhere between 6 to 12 air changes per hour, but it does say that it doesn't necessarily mean that more than 12 air changes will result in higher containment or higher clean air coming through the space. So a lot of CFD analysis has been done in lab spaces because they vary so greatly in the type of equipment that's there, the type of layout, where the diffusers and exhaust grills are all located. So if any of you guys get a chance to go to or have heard of I2SL or the International Institute for Sustainable Labs, that's a great conference where a lot of researchers and engineers do CFD analysis on labs depending on the layout, size, equipment, to determine what the best air changes is. And ultimately the consensus is there is no one right answer for all for all lab spaces. It really just depends on an application to application basis. And that's what ASHRAE Lab Design Guide does say, and same with ANSI Z9.5 that says an air exchange rate cannot be specified that will meet all conditions. But for the most part, 6 to 12 is a good starting point and can also always be adjusted as needed on site if you're finding that, that 12 air changes isn't adequate or even 6 isn't adequate. Another thing to keep in mind when you're looking at lab spaces is thermal conditions, or thermal loads, sorry. So this is essentially a requirement to ensure that the space is properly conditioned as you have a lot of heat sources in a space. So in lab spaces, you can have lots of occupants, lots of equipment or storage that is generating heat, and then even potentially windows that are directly facing the sun, which can cause that room to heat up as well. So the ASHRAE HVAC Applications Handbook does have recommended formulas like the one shown here to calculate what the airflow is in order to ensure that you are washing your any heat sources and making sure that that space is properly conditioned and is not overheating. And we'll go through that example or a calculation example for that as well. So just starting off with our example here for designing a specific lab space, like we discussed, the minimum ventilation rate for labs are typically driven by, one, the primary containment device, so the fume hood itself, the dilution and displacement of contaminants, so the air changes in that space, making sure we wash enough air into the space and it gets exhausted, the control thermal environment, so accounting for the different thermal loads and heat sources in your lab. And then the last one is space pressurization. So offset control versus pressure control and the degree of what the magnitude of that pressurization. So we're going to take a look at an example lab here that's got one supply, one general exhaust, and 6 variable air volume fume hoods. And what we're going to do is we're going to calculate the airflow requirement for each of these conditions. And then we're going to put that into a balancing table, balance out our room to determine what the airflow valves and the sizes that are required in order to meet each of these conditions. So the first one is looking at the minimum air changes through the fume hood. So we're going to use the ANSI Z9.5 recommendation of 150 hood air changes per hour, making a couple assumptions of the dimensions of the hood as well. So we've got our fume hood volume, and then we're going to use that to calculate our airflow using the same equation, volume times air changes, and that gets us 107, or roughly 107 CFM for one fume hood. And again, this is the minimum fume hood exhaust airflow in order to meet 150 hood air changes per hour. Then if we're looking at all 6 fume hoods, we're just going to multiply that by 6 and get 640 CFM. So now looking at our room, the minimum exhaust airflow for all 6 fume hoods in that space should be 640 CFM. The next one we're going to look at is the room air changes itself. So we're going to use 8 air changes. It's just in between that recommendation ANSI or the ASHRAE Laboratory Design Guide. And then we have assumptions about what the room size is. Again, using the room volume and using the same airflow calculation, we get a requirement of 835 CFM required general exhaust in order to meet 8 air changes. And sorry, let me clarify, not just general exhaust, the total exhaust in that space has to be a minimum of 835 CFM. The next one, let's take a look at our thermal loads. So we're going to use that same calculation that I showed earlier from the ASHRAE HVAC application guide. We're going to assume that our thermal loads are around just over 15,000 BTUs an hour, and that's going to include a maximum number of space occupants, all the lights being turned on, all the equipment being turned on as well, and then let's say the maximum peak solar load through that window, and we'll pretend that that window is kind of the fourth wall here. And then we have our supply air temperature and then the target room temperature as well. So using that calculation there, we can see that with all the thermal loads at their maximum or at their peak loads, we're going to need a minimum of 700 CFM supplied into this space in order to wash over all of that equipment and condition that room so it is still comfortable. The last thing we're going to take a look at here is the space pressurization. So again, we're going to assume this is a negatively pressurized lab, so we know our exhaust is going to be greater than our supply. And typically room offset, there is no one defined number for it in any of the standards. For the most part, it is just kind of a best practice number, something that maybe you're used to using, or even just a guess and check type number as you balance your room and make this more of an iterative process where maybe you try 200 CFM, room doesn't quite look right, or the valves are sized a little bit too large. Then you can always go down to 100 CFM, or if you've designed to 200 CFM and once that room's been installed, they may have to make small adjustments based on leakage rates. So we're going to assume that we're going to use 200 CFM per door. There's only going to be one door in this space. So the minimum exhaust airflow that we need to maintain a 200 CFM offset is going to be 200 CFM, because we're assuming that the minimum requirement, that means your supply is at 0. So in order to get a negative space, we just need to be exhausting 200 CFM. Again, this is the minimum requirement or the minimum exhaust airflow. So we've got all those values based on all of those different considerations for the space. The last thing we want to consider now is the maximum fume hood airflow. Because fume hood labs are driven by their fume hood, airflow, we have to take into account what the maximum amount of airflow that may be required in the space to keep it safe. So here we have an example of a fume hood. We're going to be assuming that the working height is at 18 inches in its normal occupied mode, and we're going to target 100 feet per minute again. Using that same airflow equation like I showed earlier for the sash position sensor, we have a total airflow requirement of 800 CFM to target 100 feet per minute. So if we're assuming that there is one instance where all 6 fume hoods are open at the same time at 18 inches, the vertical sash height, we're going to need at least 4,800, or sorry, we're going to need at maximum 4,800 CFM in order to meet the 100 feet per minute in each of those fume hoods. So taking all of those values, we're going to plug them into this table that you see here. This table, we have our supply valve, we have our general exhaust, and we have our 6 fume hoods, and then we kind of have the extremes of each of these scenarios. So minimum air change requirement with all the hoods closed, minimum air change requirement with all the hoods open, and then we have the maximum thermal load, again assuming that all of the heating sources are turned on, maximum occupancy with hoods closed, and the same thing with hoods open. So to start off, we're going to start off with some numbers that we already know here. So for the for all the hoods being closed, the total minimum airflow to meet the 150 hood air changes per hour is going to be 640. So in both instances, our fume hood exhaust with the hoods closed is going to be 640. And we've just calculated also the maximum fume hood airflow with all the fume hood sashes at working height, and that's going to be 4,800. Then we also calculated our thermal load. So again, the minimum amount of supply airflow that needs to enter the space in order to account for all of the maximum heating thermal loads in our lab. So that's going to be 700 in these maximum thermal scenarios. The next value we have here is the dilution displacement of contaminants being 835 CFM. Again, this is based on the minimum 8 air changes per hour that are required in that space. So we just need to make sure that the total general exhaust to meet these minimum air change scenarios is at least 835 CFM. So when we look at the first scenario here, our fume hood exhaust is 640. So taking 835 and subtracting it from 640, we get 195 general exhaust. So our total exhaust in this scenario is still equal to 835 CFM. When we look at the scenario with minimum air changes and the hoods being open, we can see here that the fume hood exhaust is 4,800 CFM, which already exceeds the 835 CFM. So in this case, we can just leave our general exhaust as 0. We don't need any additional exhaust leaving that space to maintain that 8 air changes per hour. The last thing we're going to take a look at is the space pressurization. So again, this is a negatively pressurized space. We know that the offset is 200. So we know that the total sum of the general exhaust and fume hood needs to be 200 more than what we have in the supply. So we're just going to fill in the blanks here, and that's what we get. You'll notice that in the last scenario here, we have a negative value. So this negative value is essentially impossible. So what we need to do is we need to make this more realistic and then balance the rest of the valves in the space accordingly. So the minimum number or the minimum value to make the general exhaust realistic in this scenario is going up to 0. So just having your exhaust being closed. So what we need to do is, since we're increasing the exhaust by 3,900, we also need to increase our supply by 3,900 to ensure we're still meeting a total offset of minus 200 CFM in this last scenario. So making that adjustment here, we can see that the general exhaust goes to 0 and your supply goes to 4,600. Summarizing that table and just taking the min and max flows of each of those scenarios, this is what we get for what the min and max flow ranges needs to be for each of the different airflow valves. And assuming we have a medium pressure Venturi valve, we can safely say we can use a dual 14 size supply valve with a single body size 8 diameter general exhaust valve, and then each of the fume hood exhaust valves can be a single body size 10 diameter. Now this is what I meant when you can get into more of an iterative process. So in this case, the general exhaust valve would have to be a specific shutoff Venturi valve. But if you didn't want to quote a specific shutoff or use a shutoff valve and just want to use a normal valve body, you can change this general exhaust value to 35 in your balancing tables instead of 0. And just like we did in that last example, offset your supply by that same amount and just double check that that new supply value still falls within the range of the supply valve you originally checked. So just want to touch on a little bit of the cost analysis between the difference of between a constant volume fume hood and a variable volume fume hood. So we are seeing the industry move more towards variable volume fume hoods anyways, but in the case where it's not, you can see here where we assume that the sash is only open 8 hours per day, and again using the cost per CFM as per ANSI Z9.5 being $3 to $9 per CFM per hour, or sorry, per year. And then using the same fume hoods in our example where we're targeting 100 feet per minute, so we require 800 CFM. And then if we were to use a variable air volume fume hood and target 60 feet per minute, we would only need a 480 CFM through that hood at those times. So again, going through all those numbers and looking at the total annual hood operating cost, if we were to take the extreme values at $9 per CFM per hour for all 6 hoods in this example, you can see that we can save over $11,000 per year for just these 6 fume hoods. And this is giving a pretty generous, estimate of the fume hood being used 8 hours per day. So that's saying like all throughout just the whole time that someone's working. So the last thing I want to touch on here before summarizing these two presentations here from the two sessions is the measurement versus monitoring versus control. And the main takeaway for this talking point here is just the different types of equipment and the locations that they can be required in. So the first one here is measurement. So this is specifically a room pressure sensor. So this is what's actively measuring the differential room pressure in a space. Just the sensor itself, you won't actually see the reading or know what it is, but this is really important because when you're looking at the reference, so whether you're referencing the space itself and a corridor, or again the space itself and then adjacent space, or what that reference is. So the location of this measurement is critical. The next thing is monitoring. So this is where we're actually taking that value that's being measured and displaying it somewhere or reporting it somewhere. So the purpose of the monitoring devices is to provide a visual indication of room pressure. There are so many different types of monitors. There's ball and tube versus digital. There's local versus remote, or even off-site. So local would be something at the door, like you can see at this top right picture here. Remote would be something at a nurse's station. Off-site would be, again, a cloud-based type of monitoring system. And there's also lots of different options for different monitors. But in the lab standards, it doesn't necessarily say that a pressure monitoring device is required in all applications. So ANSI Z 9.5 does say that only if the space is deemed critical should you be required to provide a indication of improper airflow and direction. But it doesn't necessarily define what is critical in this context. And then the ASHRAE Laboratory Design Guide just says that a room pressure monitor with an alarm can be provided to verify room pressure, but it's not necessarily, doesn't say that it is required. So for the most part, we don't see monitors in labs too often just because they aren't required by the standard, but again, it will always come up to end users or owner preference. So the last thing is the control. So the control is now where we're actually using this measurement and not only displaying it or reporting it, but we're doing something with it. So this is where we're using our direct pressure control for room pressurization, where we're using that room pressure sensor, relaying that back to the controller, and then that controller is going to be adjusting the airflow valves accordingly. So when you talk about measurement, you just want to make sure that your reference spaces are accurate and the location of the pressure sensor is exactly where you want to be measuring that differential pressure. When you're looking at monitoring, you want to make sure that the location of where you want the pressure to be displayed is properly shown as well, whether it's local again, remote, or if it's through the BAS. And then control, you want to make sure that you have some sort of control device that can take in that pressure and then do something with it. So lastly, just some design considerations and challenges in critical spaces. So it is not very, but it can be challenging to identify the different chemicals going through fume hoods. Like we talked about on Tuesday, depending on the types of fume hoods, concentrations, and the frequency that they're being used, you're going to need different types of coating on your airflow valves. Establishing a minimum air change rate to suit each specific lab application. Because this isn't defined in the standards as a hard number or as a minimum, this can be more of an iterative process or a guess and check type process. And then achieving energy efficient design without sacrificing safety and performance can also be a challenge because the owner's primary goal is of course to save money, but the aspects of safety may not be abundantly clear when we're initially designing systems. And again, here's just a summary of the different closed loop and open loop devices that we reviewed today and both on Tuesday in session 1. One thing to note is just because we do group each of these technologies in open and closed loop, it doesn't mean that they are fixed to only be working with other open loop type of devices. So a Venturi valve can still be used with sidewall velocity control in a space with pressure control. So you can mix and match. This definition or this table doesn't define when you should use each application. It just defines how these devices work on a fundamental level, just how their technologies work. But in lab applications, we do have typical recommendations. In labs, we do recommend Venturi valves for some of the reasons that I mentioned earlier, that mechanical pressure independence, that instantaneous speed of response to changes in duct static pressure, and also the higher configurability when you're looking at different types of equipment control. And then fume hood control will highly recommend on the type of sash type. And then, like I mentioned, in room control, we typically recommend volumetric offset because it's just quick and stable, especially when you're considering labs with lots of variable volume fume hoods.